In this video, we'll prove this result. In the first part, any minimal polynomial in fx satisfied by a in k, where k is an extension of f, is an irreducible polynomial in fx. And in the second part, we'll prove that if an irreducible polynomial over f has a root a in k, then it is the minimal polynomial. That is, irreducible plus root should give us minimal polynomial, and minimal polynomial is always irreducible. So minimal always implies irreducibility. Minimal implies irreducibility, and irreducibility, that is irreducible polynomial satisfied by a. So this must be there, should imply that polynomial, irreducible polynomial, minimal polynomial is irreducible polynomial first case. And here irreducible polynomial with a as a root should be minimal polynomial satisfied by a. So that is what these are the two substitutions that we are going to prove in this result. So for the first one, let p of x be the minimal polynomial and fx satisfied by a, then p of a is 0. Now we claim that p of x is irreducible. Suppose not, then p of x is r of x into s of x with the degree of r of x less than degree of p of x and degree of s of x less than degree of p of x. Now since p of a is 0, r of a into s of a must be 0. But these are elements in f of a, which is a field. So that's an integral domain, because every field is an integral domain. So product of 2 equal to 0 should imply either this one 0 or this one 0. In either case we get a contradiction, because p of x is minimal polynomial, which means you cannot find any other polynomial whose degree is less than degree of p of x satisfied by a. But we are getting r of a to be 0, which means you have a minimal polynomial, a polynomial whose degree is less than the minimal polynomial satisfied by a. So this contradiction tells us that p of x should only be irreducible. We assume that to be reducible, and we have got a contradiction. So it must be irreducible. Now for the second part, we shall assume that p of x to be an irreducible polynomial over f satisfied by a and k. Now we'll have to prove that this is minimal polynomial. Suppose there exists some other polynomial, say q of x satisfied by a. So q of a is 0. Now if you are able to prove that degree of q of x, any other polynomial, is greater than or equal to degree of p of x, means p of x has to be the minimal. Now suppose this is what we claim. Suppose we assume that degree of q of x to be less than degree of p of x. This is our assumption. Now you consider your psi from fx to f of a defined in this way. This is evaluation homomorphism. We can easily prove that psi is a homomorphism. That will also be discussed in one of the videos. So for the time being, I'm just stating that this is a homomorphism. And when we find the kernel, it is all those functions in the domain which are mapped down to the 0 element of the codomain, that is 0 here. But evaluation homomorphism, so h of a will be 0. All those h of x for which h of a is 0. All those polynomials which vanish at a. Now we consider an ideal b generated by p of x. P of x we have already assumed, so that is irreducible polynomial, and any ideal generated by irreducible polynomial is maximal. Because fx is a Euclidean ring, this result holds. So this is maximal. And p of a is 0, means p of x should be a member of, because this consists of all polynomials which vanish at a. And p of x also vanish at a. Therefore, p of x must belong to kernel psi. So that means what is the relation between v and kernel? V must be contained in kernel, but kernel is contained in fx. But we know that v is maximal, so we must have v to be kernel psi. Why kernel psi cannot be fx is, you have one to be a member of fx, but one is not a member of kernel psi. So the equality between these two is not possible. So you have v to be kernel psi. So And q of x, because you have q of a to be 0, q of x should belong to kernel phi. Kernel psi is all those polynomials which vanish at a. Q of x vanish at a. So q of x should be there in kernel psi, which means q of x should be b is generated by p of x, so q of x can be written as some r of x into p of x. But this is a contradiction to statement P, in which you have assumed that degree of q of x to be less than degree of p of x. So your degree of q of x should be greater than or equal to degree of p of x. So this in turn implies that p of x is minimal polynomial. You can, if you consider any other polynomial, then that has to be greater than or equal to, that the degree of the polynomial should be greater than or equal to degree of p of x. So p of x should be minimal. If you have q of x to be equal to degree of p of x, means r of x, they are the same. You will get them to be the same. But when you have degree of q of x to be greater than degree of p of x, this one, that is our claim. If you assume this, then you will get a contradiction. Given degree of two polynomials, the possibilities are there are three possibilities. One is greater than or less than the other, and then they are equal. So this one, if I assume that I am getting a contradiction to this, so there is no other go. We'll have to have this only to be true. So that concludes. From that we are able to conclude that p of x is minimal polynomial. So whenever we have irreducible polynomial satisfied by a, we cannot simply say irreducible polynomials are minimal polynomials. It should be satisfied by an element, and for that element we will have minimal polynomial. So those two will be the same. So that is what we mean here. Thank you.